Yeah. Welcome back. Today I'm going to finish the sparse extended information filter. And the second part of the lecture will be on a bit of recap on all these Kalman filter-like filters. So all this family that we've seen, Kalman filter, uncentered, extended Kalman filter, the information filter. So all of these approaches that actually considers the Gaussian as the underlying error distribution, and they have normally linear or not too strongly nonlinear models, both from observation and motion models. So what we've seen last week on the sparse extended information filter, we stopped here. So we have seen how to do the motion update and how to do the measurement update. What we're going to see today is how to do the update of the state estimate, at least partially, because we'll see that this will remind, there will be like a pointer to the end of this lecture. So to the end of the whole set of lectures, because there is a way of computing this. Actually, we'll see it later on when we talk about optimization-based lamb. And then we'll see how the sparsification works and how can we compute the sparsified information vector information matrix. So what we need to do is, as we said, recovering the mean. And we need it because the mean is useful for linearizing both the motion model and the observation model, because these Jacobians needs to be evaluated at a certain point, and to have the effect of nonlinearity quite limited, we always evaluate them at the current mean of the state vector. Okay, so normally we don't have the mean, so we need to recover that. The second reason that we want to use it is also for the sparsification step, because we might need it to re-evaluate the approximated information vector that we get. Because we're going to do some operation on the state space, on the random variable, to get an approximate distributions under the model that we are approximating, so cutting a bit of correlations between the various landmarks. And from doing this, we need the mean for getting the new information vector. So how do we recover it? If you look at the motion update, we have already a predicted mean for the after the motion, because once we have a mean from our previous step, we know from the Kalman filter that the optimal prediction is just applying the motion function to the mean. So we just do an update, and what you see here, the previous mean plus this, is basically the meaning is the application of the motion function. Now, this will be our delta in the motion. This is the that comes from our nonlinear function. This is just a usual f that puts it back into the higher dimensional space where it is mean and landmarks, and then we add it up to the old mean. Okay, so the nonlinearity here is actually masked in this delta here. And this is the optimal prediction, and that's what we're going to use when we want to evaluate the Jacobian of the measurement function at the point. Now the problem is how do we get this mean after we do a correction step? And that's the more problematic part. And what we do is, in principle, we know this relation. Okay, so we know that the mean is equal to the inverse of the information matrix multiplied by the information vector. Okay, the problem is we know this is sparse, but it still contains a lot of numbers. So in principle, we might just try to use some sparse inversion of the matrix, but what actually is going to be done is you solve this as a set of as a linear equation problem. So you can see here in terms of I have my unknowns, and these are equal to the inverse, but you can also put it on the other side, which is probably easier to see. Basically, we have that our information vector is equal to the omega times the mean. And if you see like this, these are our unknowns. This defines a linear system of equation, and you have, this would be the value. So it's something like a x1 plus b x2 equal 3, for instance, or so. No? And these are all stacked in here. The A and B are actually inside omega, and X are the one in the mean that we are trying to compute. No? So in reality, you don't really do this. You don't invert the matrix and multiply by the information vector, but you solve these equivalent linear systems. And we'll see later on that actually you cannot really do this because there are more equations than unknowns. So it's an over-determined system that does not always admit a solution. So what we do is we formalize, or we cast this as an optimization problem, where we say we need to compute here normally 3 dimensions because that's the one that you need for linearizing. So it will be, if you need to do a linearization for the state vector, you just need to solve for x, y, and theta of the robot, or if you're in 3D with the z and the different angles. If we need to linearize all around some landmarks, you can also solve for just a few of them. But in general, you can either decide to solve for the one that you need, or you can decide to solve it for everything. But the whole principle is to have it as a minimization problem, or in this case, a maximization problem. So we get this here is the expression of the full distribution, full joint distribution that we have in terms of a Gaussian, and this is our information matrix. And this here is the form that we have if we consider it in the canonical representation. No? So we know a Gaussian to be expressed in this way. We have some normalization factor, exponential of minus, and we have x minus mu transpose sigma minus 1 x minus mu, and this is 1 half. Okay? So that's the normal Gaussian representation that we remember. Now, when we go on the canonical representation, so the one with the information matrix and information vector, what actually happens is we open up this whole product and we rewrite it in terms of something which is like this. There is some constant that we don't care for now, and you can then write it as minus 1 half, and then we have the mean omega, which is the inverse of this, times the mean, plus, so let's write them as before, so it will be x transpose x, and then we have the linear part, which is then eta transpose x, okay? Where this eta is actually equal to omega mu, okay? So that's the canonical form, okay? And it's called also, so it's a different way of expressing it. They're just equivalent, and there is this equivalence here, and the part here that you have in the constant is the whole multiplication of mu, sigma, and mu, because it doesn't really depend on the variable that we're considering, which is the x. Okay? So if you write it like this, we can also write it inverted in this way. And what we're trying to do is trying to maximize, in that case, mu, but will be the equivalent of this x here, trying to find the mu that maximizes the likelihood, or this distribution in this way. No? And what we normally do is we take the negative logarithm of this. So we just then remove the exp, this becomes a plus, and we try to minimize this part here into a least squares problem. Okay? But we'll see how to do this later on in the class. Algorithm for doing this, just to give you a bit of a sneak peek. The main idea is that we take the derivative of this function that we want to minimize, we set the derivative to 0, and we know that this is a stationary point, and since this is a quadratic function, then the stationary point is the minimum, because it only has one stationary point. Yeah, and then we can iterate, because there is no linearity involved, so we can recompute the information matrix with the new linearization point and so on, and we just end up in the global minimum of, or let's say in a local minimum of the nonlinear function. There are a lot of tricks and algorithms for doing this, and we'll see them at the end of this class when we talk about least squares lambs and graph-based optimization approaches. But for what concerns you, you can just say there is some way of computing it, and I will know it later on. And that's basically it for computing the mean. The trick of having this efficiently is because the mean is computed at every step. So the solution that you have at the step before is a very good solution. And since we have iterative methods for computing, for minimizing this system of equation, this least squares problem, whenever you're very close to the solution, the number of iterations is really small. The matrix is sparse, so you can have a very quick iteration because of the sparse matrix. You don't need to compute too many things because you can reuse computation that's been done in the step before. And that's the trick why this whole thing actually is efficient at the end. Okay? Any questions so far? Okay. So the last thing that actually is left to explain is the sparsification. And this is a bit, it seems involved from a equation and everything which is there, but it's not that involved once you understand what actually the equations are saying. So let's see. So first of all, do you remember what we said about what we sparsify and what it means to sparsify the information matrix? Does anyone remember what's the implication on that? No? So you remember we had this nice graph where we had like the robot here, it was connected with the landmark, then was connected with another landmark, then there were some landmarks, and we said we wanted to remove like these connections here, no? And which equivalently means that if we have our matrix, which is something like this, where we have this part here, which is all somehow grayish. What were we doing in here? We said we wanted to put some zeros, no? So we just want to make this and this, for instance, equal to 0, right? And do you remember what was the relation between this matrix to 0 and the graph? There was some independence relation, right? Does any of you remember which this meant? Okay, it doesn't matter. I will tell you. So the meaning here is that we basically impose some conditional independence, okay? So intuitively, it's saying we are ignoring the correlation between these two variables. So in this case, by removing what's in this cell here, it means that before the landmark M1, in this case, was related to the pose of the robot. When we cut it out, we are saying that the landmark M1 is not related to the pose of the robot any longer. So if you remember, the meaning of this matrix, the information matrix, was a matrix that was telling you conditional independence between variables. And basically, this is saying if there is a 0 here, it means that this variable is independent from this variable given all the others, or also vice versa, is independent of this variable given this. No? That's where this kind of relation comes from. Because 0 means that there is no relation between them. And so if you look at the conditional independence, you take this, you look at this column, and you know what is conditional independent and what is not. No? So that's the relation there. And that's what we are trying to exploit. So basically, we are transforming weakly conditionally dependent variables into conditionally independent variables. So that's the whole principle there. What does it mean, conditional independence? It means this. Imagine we have this distribution, so we have 3 variables here, and we have a joint distribution between them. And we can say that A and B are independent given C, so conditional independence. If we can write the distribution of the density of A given B as C is equal to the density of A given C. Okay? So basically, we can cut out the B here because it doesn't influence A once we know the value of C. And the same is if you flip everything, because independence is symmetric. So we also say that the density of B given A and C is independent of A. So it only depends on C, okay? Which turns out that we can then now rewrite this distribution with this assumption in a easier and nicer way. We can say that normally we can just use the chain rule. So we can say that this distribution, the joint, is equivalent to the distribution of one variable given the other two, the second variable given the third, and the third variable. If we assume now conditional independence here, we can just approximate this in the product of these three terms. So we remove B from here. And if you play around a bit with some mutual tricks up and down, basically this ends up that we have two joint distributions of a lower dimensional divided by a third one. Okay? So that's somehow how we can approximate everything. This, again, is an approximation because it's not, there's no equivalence between these two. They are only equivalent given the conditional independence. And in this case, we are enforcing conditional independence. So it's not in the variable themselves at the beginning. There might be the case that these are really conditional independence if you know them, and then there is an equivalence between the two. Okay? But for sparsification in Seif, we are enforcing it. So there is no, we are losing some information. We are losing accuracy. We are approximating our target distribution. Okay? So the idea, again, just to really enforce all of this, is that we only maintain links between the robot and the few selection of landmarks. Okay, so we try to keep this dependence between the robot pose and the landmark kind of constant, because if we know that this is constant, we can ensure constant time updates on the step of the sparse extended information filter. And so the only way to do this is we consider the one that you're observing right now, which we call them active, as you remember before, and then we remove the one that goes away out of our vision, field of view, and we just keep a limited number of them. Graphically, it means, again, this you have seen also at the beginning of the class. It means if this is the robot, these are the active landmarks, so they are the one that is observing right now, and they're also the one that are kept correlated, so dependent with the robot pose. We have a set of landmarks which are considered passive in this case, and you can see that there are still links from the passive to here. So this is still kept, but what we do is that after the robot moves on, we somehow cut some of these active landmarks, so we put the zeros in the we don't really put directly the zeros. There is a way of computing a new information matrix that actually model the approximation that we do, and turns out that we are just cutting things there, and we'll see it later on what does it mean. And then we get a new this new distribution. Okay, so remembering the active one is just a subset of the landmarks that we have. And we always include in this subset the landmarks that we are observing right now, okay? Because removing them basically means I'm not just approximating the distribution, but I'm completely neglecting the current measurements, okay? And that's something that we don't want to do. We just want to get all possible information from the measurements, and we just want to get rid of weak links, weak correlations, okay? And the passive are just all the other landmarks. And then we have, before this restarts, so we can now see and decompose the set of landmarks that we have, so our map, into three sets, okay? The active one, we discussed them already. These are the landmarks that are observed right now, and the few selected ones that are kept active while the robot is moving. We have the passive landmarks, which are all the rest. And now we have another set of landmarks, which are the ones that were active at some step, and then they become passive at the step after that. No? So that's where the sparsification is happening, because without this, we just commit to a set of passive and active, but we don't know when one goes to one set or to the other one. Okay? And the idea is that we somehow have to transfer the information of this to either partially here or partially there to keep the information content as in the best way possible. Okay? So how do we do it? There is an approximation that we use, and the concept is we try to enforce conditional independence between these landmarks and the robot pose. If you now see how this influences our distribution, is we have, this is our joint distribution, so the pose of the robot and the map, so which is all the set of landmarks. Right now I'm removing all Z and U just to avoid clutter. And we can rewrite them in the tree set that we defined before. And we can see that this can be decomposed in a lot of different parts. So with the joint, it becomes a conditional times the joint of all the landmarks. And what we do here is we are considering the passive to be 0. We don't really need to do it, but it simplifies some computation. And the point is, since they are independent from the robot pose, so there is no connection of the passive landmarks to the robot pose, they also do not influence the pose, the estimate of the pose. Therefore, we can just put any value there and everything will not change. In principle, we can also cut it out because there is some independence there, but we just keep it here for showing that they are there somewhere. Okay? How do we approximate it? We approximate it by putting this M0, so this active, landmarks that goes from the active to the passive one. We move them into the, in principle, we move them in here, but for clarity, here we can say since they are independent, so we put this conditional independence with the robot pose, then the distribution of X doesn't depend on M0 given M plus. Okay? So that's the whole concept of conditional independence. What we've seen before with A, B, C, we had something with 3 variables, it was B and C, and then we removed one of them. Okay? So that's the same reasoning that happens here. And this is the only approximation step we do. This other part, the joint distribution of all the landmarks, stays the same. We don't have to change it. And now we'll see how this will then come up in an update rule of the information matrix and of the information vector accordingly. So if we do some more tricks, we can rewrite this into the join, so we put M plus in here. And for doing this, we need to put the normalizer down there, which is the density of the active landmarks given the passive one. Okay? And this is our new approximated distribution. Okay? We write it in this way because it's easier to find the distribution of these two joins rather than the other one. But in principle, you just need to, if you are able to find update rules for this and this directly, you don't need to do this trick. But in this way, it's actually easier and shows you what's the structure and why some values in the information matrix goes to 0. So now, if you put also the Z and everything together, we have this, our distribution. And as you can see, it is one density divided another density multiplied by a third density. Okay? So if now go back on how the information, so the Gaussian distribution is constructed per se, we have E at the power of minus something divided by E at the power of minus something else, okay? Which then, since it's a linear combination, it's a quadratic form on the exponent, we will have that the exponent here gets minus the exponent down there. So we will have this omega here, which is the information matrix on the upper part, minus omega 2, which is the information matrix of the lower part, times this, so the exponents sum up. So we have times omega 3, which is the information matrix of this third distribution. Okay? So to update the new approximated information matrix, we just need to compute these 3 quantities, sum them up in this way, and that's how we that's our update rule for the sparse extended information filter. Okay, so I'm trying to get slow. If you don't get some of the passages, just raise hands and explain. Yeah, so this is the connection between the three. Now, how do we get there? So what we have, it's probably good to do it on the whiteboard in this case. So what we have is this distribution. No? We have P of x, m plus, m minus, m0. No? So that's our original distribution. And we can say this one gets associated with omega, which is our original information matrix that we have before the specification step, no? Which will be this one on top here. Now, if we want to get the upper part, okay, so we just need to do two steps. First, we need to get rid of m0s, okay, because it doesn't appear there. And getting rid of a variable in probabilistic terms means we have to marginalize this distribution with respect to this variable. And then we have to move m minus on the right side. So we need to condition this distribution on m minus, okay? So the first thing that we do, because it's used in two different steps, we just do the conditioning first, okay? Conditioning in canonical form means we just need to take the blocks of this matrix that belongs to the variables that we are considering, okay? So let's say we do a conditioning on m minus. This gives us this distribution, P of x, m plus, m0, given m minus. And this is associated with omega 0. That's how we called it there. Okay? Now, we still have nowhere on what we need, because this distribution is nowhere in there. But we have the upper part, which is very similar, because it's exactly this when we marginalize m0 out. Okay? So then we marginalize m0, which is the integral of this. I'm just writing the same in the m0, which is again p of x m plus given m minus, and this is associated with an omega 1, which is the first part that we actually consider here. Okay? So that's the first step that we do. Then we take again m0 and we marginalize x and m0 to obtain the one below here. So as you can see, we can just go from directly this one and do a marginalization on this on top with respect to x. So we do the marginalization of x, which is equivalent of p this one. So we'll just put an arrow in the x. This gives us the density of m plus given m minus, and in there we note it as omega 2. Okay? And the third step is here, where we get the original distribution and we just marginalize x out of that. Okay? So we then again marginalize x, which is our usual integral of p. In this case is the first one, so let's write everything, m plus, m minus, m0 in the x, which is p of m plus, m minus, m0, and gives us our nice omega 3. Okay? So once we have all of them, we just do the sum and differences of them, and we are happy. Now, it's not exactly like this, because these are all, if you just do that, they're all in a different low-dimensional space. So these matrices actually are the high-dimensional embedding of the one that we've seen before. Okay? So that means that we'll have the same form with respect to the variable that they are considering, and there will be zeros all over the place to consider the fact that they're just the projection on a higher dimensional space. Okay? So that's the framework. And to get then the information vector, what we do is we apply the definition of the information vector, which is information matrix time the mean. We get the mean because we covered it in the previous step. And what we do is just, we say the new approximated things is like this. So it's basically the old information matrix minus the old information matrix plus the new one, which basically means that we get the previous information vector, and here we have the new information matrix minus the old information matrix times mu. Okay? So this is basically saying I remove the information of the mean that I had before, and I add the new information of the mean. So that's what this thing is saying. And then I take the previous information vector that I had. Okay? And the same thing is where we did it for, in this case here. So the zeros happen because when you, from omega 1, you remove omega 2, in omega 2 are actually all these off-diagonal elements that we want to remove. And if you look exactly at the structure of the matrix, this will be the same value on the off-diagonal that you have in here. Okay? And this kind of matrices also have a specific name in graphical models literature. They are called cutting matrix, and they are really made in a way that the off-diagonal terms are so the same values as the link or the conditional independence links that you want to cut out. Okay? Because what happens is we modify a matrix which is mapped to an adjacency graph, and whenever we have zeros, it means that there is no edge in the adjacency matrix of the graph. Okay? So that's the whole idea on here. And this third part here is somehow putting back the information up there. Okay? There are several ways of coming up with the same approximation according to how you choose this and how you choose these distributions, but that's the way it's also explained in the book, and that's how I'm telling you this. And it's also the one maybe easier to understand in some way because you have a clear representation up here on what's happening on the, at the individual steps. Okay? Now, if you go more into the detail, as we said, here is a kind of a sketched representation of what's happening. What really happens is that we need to consider this F here, okay? These are all these matrices, the same that we've seen for the Kalman filter and for the extended information filter. These are the matrices that actually either lift your low-dimensional matrix in a higher dimensional one or project it down there, okay? So the way they are made is that each F is somehow made in a way where there is an identity matrix here that has the same dimension as the space that you're considering and as the zeros at the right place. And then there is a 0 down here and a 0 down here, or sometimes there is an I and so on. Okay? So they're all made in this way where all these matrices somehow are embedded in the low-dimensional parts that you want to extract. Okay? The effect is this, is that when you do F transpose a vector, let's say, you are just extracting the elements that you care, and they were indexed by F. When you do F transpose a matrix F, you are extracting the blocks on this matrix that are related to the elements where there are ones in F. And instead, if you do F x, so now there is no transpose, you are taking a low-dimensional vector and you are embedding it in higher dimensional space, and this vector will be the same vector as before, and whenever there is, in the other part of the resulting vector, there will just be zeros. Okay? So it's really like one low-dimensional point on a higher dimensional space. Something like this point is on this line in here, and now we are imagining that there is another dimension here and another dimension there. The point will still lie there, and therefore, if you look at the coordinates, they will have a 0 coordinate on the z and a 0 coordinate on the x. Okay? It just stays on the y there. And that's what this F does. And the same is if we do F omega F transpose. It's the same thing. This is a low-dimensional matrix, and we just put we increase the dimension, we just put zeros in the parts that were not spanned by this matrix before. Okay? So that's what they do. And the reason that you have F times F transpose, times omega, and so on, it's because you first extract the part that you care in omega, and then you reproject it back up into the higher dimensional space. So these things It's just a way of saying I'm putting zeros in the part that I don't care about. Okay? And you can also see it if you just multiply F by F transpose, no? Because if you do something like this, you do F times F transpose, and our F has a structure like this, then you take something like this, and you will end up that this one is equal to identity 0, 0, 0, 0. No? If you just multiply them with each other. And this is exactly what's called the selection matrix. So this is a matrix that selects certain blocks or certain elements when you apply it with a matrix here and a matrix there. Okay? Any question on that? Okay. Now, to go on the specific here, whenever we put these things down there, it means that's what we are selecting. Okay? And that's how you can interpret now this algorithm here. And if you remove all the F, it's exactly what we wrote down here. And the F are just building up the matrix. So we do omega 0, which is computed like this, which is just, as you see, the conditioning on X, the conditioning on M minus of the whole state space, because we are just extracting the one that we care about. And that's the definition of conditioning in information form. And then we have this here, from here to there, which is the one associated with, let me think, like 0, you marginalizing M0. So this is the one which is associated with the marginalization of M0 out. If you go back here, will be this, and we call it omega 1. Okay? Then we have this second part here, where we do, again, a marginalization. So if you, okay, I have to go back a step before. Do you remember how to do marginalization in information form? Okay, so let's do it here, because we go, otherwise it's a bit hard to understand why there is a minus up there. So when we have two variables, let's say A and B, okay, this is our information vector or so. Then we have our omega, which is now done in omega A, omega B, omega AB, omega B, AB transpose. No, they're actually the same because the matrix is symmetric. Conditioning is just, we take the block that we care about. Marginalization is done by what's called the Schur complement of a matrix. So we say that the marginalization of, let's say we marginalize B, okay? This basically means we take our omega A, and then from this we remove omega AB times omega B minus 1 times omega AB transpose, okay? So that's the definition of marginalization in information form, okay? And that's what's happening in here. So this one minus this, if you see them on a higher dimensional space, there is 0 everywhere, and it's just taking the part where is the omega that we care and is removing that thing, okay? Does it make sense? So you see the parallel at least, no? And this will be this omega 1 here. So the fact is we are taking care of everything. So we are computing this with respect to the upper part. This will actually be omega A, okay? So we are computing this, and then we have to consider the fact that when we bring it up, this will just be this part here on the top. So it will be something like this. Let's call it omega star. Will be omega star here, and then we project it up. So it will be 0, 0, and 0. Okay? And our previous matrix is done like this. We don't want to change parts of that. So we only want to change the part that we really care about. And therefore, we can put the omega star here, or we can keep as it is before, and we'll just do the minus of this part up here there. No? So there will be then omega star only this one. Okay? Because here we have anyway omega A, and that would be then omega B. So up here we still have what we care about. Okay? So that's the idea of this. And the same we do with another Schur complement here when we marginalize x and m0. Now the sign is flipped because this was the minus m2, minus omega 2. So we take it on the other way around. And then we do a final marginalization here with respect to x, which is omega 3, and we still have the minus there. Okay? So the fact that we only keep one omega here and we don't do the different omegas is because each of them actually works on a different subset, so we can just play around with that. No? Because this marginalize on basically, yeah, okay. So the thing is, just trust me, but this is just a simplification. When you write down the right marginalization there will be an omega part here, an omega part here, and an omega part here. When you sum up all the three different omegas, you get the original omega back. So it will be just summing and sum and minus of the same thing. That's why it's written in this way. And that's just to save a bit of computation. But in principle, it's really computing the three different matrices and putting them up. Okay? The information vector is updated as we've seen before. We take the old one, we take the residual information of the approximation part, and we add it up there. Okay? Any question on that? Okay. So then that's it. So that's the whole step of the Seif. It's one after each other. You need to really exactly implement the equations that have been written there, and you get your filter back. Now, what happens in practice? So how this approximation actually affects our estimate? If you look here, we have a full non-approximate distribution. So everything is connected with everything. You can see these gray lines there. This is the resulting covariance matrix, or at least the sparsity pattern of that. So the lighter, the less correlations between variables. And here is the resulting information matrix. Okay? Now, we do a sparsification. So we go from 1,300 circa measurements, so like joint dependency between variables, to something about 500. And you can see that the graph is way sparser, so there is way less dependencies between the landmarks in here. The covariance matrix has some weaker correlations in these parts. These are the parts where we actually cut some of the link in here. And they were already like, I don't know if you can see it from the light point of view, but these were already like lighter. It just exaggerates the way the values of this here. But if you look at the information matrix, you don't see much difference. Okay? And that's because the links that actually have been removed or cut out were links which had very low dependencies between each other. So there were links between variables that were weakly dependent. Okay? So this is just visually. So let's see what happens if in the estimate of the pose and then the landmark. What happened is that we are basically trading off accuracy for efficiency. Okay? We have an algorithm which is roughly constant time besides the estimate of the mean, but it's also something that you don't estimate sometimes too often, because if you're not if you're not reobserving too many different things, or if you're just moving away, the change in the estimate is more, so that you can actually devise a strategy for doing this amortized constant time. you have a linear memory complexity. So instead of storing a quadratic number of values in a covariance matrix, you can just store a linear number of values in a sparse information matrix, but you get less accurate. So the accuracy decreases, and then the amount of sparsification versus accuracy, it's kind of a trade-off, a slider that you can play to decide how much I care about efficiency and memory consumption versus how much I care about accuracy. If you look here, we have that if you increase the number of landmarks, so these are the number of landmarks in my whole map, okay, not the active or passive, but all of them, we see that the time of the AKF grows quadratically. I mean, I'm not sure if you can really see it, but you can see that it's starting to get like a parabola up there, while the complexity of the Seif starts to stay kind of constant, okay? And that's because you will always have kind of an increase of computation because of the part of the overhead and part of the amount of landmarks that you will keep in the window. So you will reach at some point like a critical number of landmarks, and then there will be so much, they will be so spread around that the number of landmarks that you see at one instant of time is actually kind of constant. Everything is bounded, and then you kind of get a roughly constant computation. I mean, this will still increase, but very, very smoothly and very lightly increase. With respect to memory usage, again, you have a linear increase in memory usage, and that's mainly because you have to store the landmarks anyway. So on diagonal of this information matrix, you will still have to add something, and also on the information vector, you still have to add dimensions, so for every new landmark that you visit. But you don't have this quadratic increase that actually you see in the Kalman filter. Accuracy, we get a bit worse accuracy, as you can see here, and the more landmarks you have in your map, the worse is so the bigger is the decrease in accuracy, because you are neglecting more and more correlations between these landmarks. But this is the error in terms of meters. You can see that the error is not drastic in terms of accuracy error. Okay, so up here we have just 4 centimeters in terms of error. So it's not a huge average error in this case. No? If you see it more now in terms of how many active features, so the plot before was when we were using around 10 active features as a number, you can see that the update time for the Kalman filter, when you use all of them, it's about 140 seconds, while you get down to 30 seconds. So this is actually an old slide from when this thing was derived. I believe it's about 2001 or so. The computer was not as efficient, so you can get better right now. But the important thing is the decrease in computation time that you have by considering 10 up to 4 landmarks. So you can see that the computation decreases over and over. But of course, on the other hand, you get worse accuracy result. So the interesting thing is here, so that's a root mean square error. So it's, let's say, the dimensionality of this is in terms of meters when we consider translational, and that's the case. You get 10 centimeters, and you see that the error is kind of negligible between the Kalman filter and the sparse extended information filter with 10 active landmarks in that particular experiment. But the less landmarks we take in the active window, the worse we get. And at some point, this will just blow exponentially up there when we consider only one landmark, for instance. Okay? So there is always kind of a trade-off in this case between accuracy. But the whole message here is that if we are somehow around here, at least, and these numbers of active features also depends on how big is your, how dense is your is your environment with respect to features, how many features you see at each time step. This was done on the Victoria Park, so they had few sparse trees that were around, so 10 was a reasonable number. You might need to use a bigger number if you have seen more features for each time step, or a lower number if you see low of them. But in principle, the message is there is a certain window where you get a reasonable level of accuracy, but also a very nice reduction in computation and memory requirements. Okay, so that's basically the whole message that Seif, they want to give you with Seif, is that we can exploit the structure of the problem, the fact that there are some parts of the environment that are only weakly related to each other, and we can devise then approximation that exploits this, and they don't lose too much in accuracy, but they gain a lot in terms of efficiency and memory consumption. Okay, so that's basically a slide that is telling you, and it's useful for the exam to, at least if I ask you what's the important thing of Seif, you can just answer these things, and I'm happy with that. Then I ask you how it's implemented, then it's your problem. So if you want to have a bit more info, that's on the book, Probabilistic Robotics. And on the webpage, I have some other pointers where points to the research papers that presents the approach. So it's a bit more in-depth analysis and discussion. This will be it for the first part. The second part is just a summary of everything. If you want, we can start it again soon, or if you want to have a few minutes of pause or break, I'll try to be on time at 6 anyway. What do you want to do? Shall we go on? Okay. Okay, so probably I can go very quickly on the summary on the sparse extended information filter. Anyway, so what we have seen in this few lecture is the family of Kalman filter. So that's one of the three main paradigms we'll see in the class, and we've seen that this actually can split up in the standard Kalman filter, the extended version, the unstandard Kalman filter, and then the two versions of the extended information filter, the original one and the sparsified version of that. Okay, so this is the Kalman filter, and the beauty of it is that it's on one side optimal if you actually can meet the assumption that you want. So linear system, linear observation, and Gaussian random noise. And on the other side, it's just made of 5 lines of code. Okay, so that's like very simple, elegant, and quite effective if you meet the assumption. When we go into the nonlinear case, so I'm not going to explain again all the steps, but you have a prediction phase, a correction phase, and you should know now by heart how to compute the Kalman gain and how to do everything to obtain the new estimate given one observation. The problem is, of course, that this is only optimal in this case, where we have the evolution of our dynamical state. It's linear, so we have something that depends linearly on the previous state, linearly on the input, and we have a Gaussian noise there. And the same is for the observation, where we can predict our observation through a linear function of our state. Okay? The problem is that we normally don't have it in a lot of physical systems, but what we have is a nonlinear function of the input and the state, and the same thing for the observation, we have a nonlinear function of the state. Okay? The way the initial way of approaching this is that we can linearize this function and then use this linearized version as an approximation of our models, and then we can still go into the same equations that we have for the Kalman filter, with the difference that we basically lose the optimality of the filter, but we just have something close to optimal. Okay? So this is one way, and this is what is called extended Kalman filter. Okay? So if we now look at the differences between the two, we can see that it's a first, actually quite popular way of handling nonlinearities for the Kalman filter. It's doing some local linearization. There are also some twists of the Kalman filter where you, for each step, you actually re-linearize multiple times. It's like, I think it's called iterated extended Kalman filter, where you try to at least get a better linearization points than your actual one. So imagine that for the motion update, you will compute the function, and then you will just slowly have an approximation. You go down a bit, down a bit, down a bit, and the same thing for the update part. But this is completely out of the scope of this lecture. But just to say that this local linearization, there are some few tricks that one can apply to get something better. And the important message is that in practice, what we have is we are building our system, okay? So we try to make our sensors and our actuators as good as possible. Therefore, we try to limit the error, the noise in the system. And this means, and we've seen it, that with low uncertainty, the approximation, the local approximation is not too bad. And in case of SLAM, we also have some moderate nonlinearity, because the nonlinearity comes from the angle. And we know that the closer an angle is to 0, so also a closer displacement, the difference between angles is close to 0, the more linear is the behavior of the angle, no? Like the sinus goes to, kind of tends to 0, and the cosine kind of tends to 1, so we are kind of close to an identity matrix, no? When we take a rotational matrix. If we have a very fast update, it means that our small differences in angles are very small, so the nonlinearities that we have are actually quite limited. And therefore, when you actually apply it in practice with a very quick update loop, it works well. Okay, so that's basically the reasoning why these things works well. And if we see now the structure, we normally have it with the robot pose here, the landmark pose there. We have a covariance matrix that has on the upper left the marginal covariance of the pose, the lower right, the marginal covariance of the map, and then we have the cross-correlation terms on top of there. And we have seen that when we do the update, the motion update only touches this part and this part of the matrix, while when we do a measurement update, we also touch the full matrix. No? So that's something we've seen when we're discussing the Kalman filter. If we look again at the evolution, this goes here. The matrix at the beginning is diagonal, but the more you go around and you observe the feature vector, it becomes fully dense and fully correlated, up to a point where it's completely dense and packed, and more often has this kind of interesting structure of highly correlated, lower correlated, and so on. And that comes from the fact that the x coordinate of each landmark strongly correlates with each other, the y coordinates of each landmark strongly correlate with each other. And interestingly, here you can see this white line completely here. Any one of you wants to give a hint why it's a complete white line there? Any idea? So look, count, no? There is 1, 2, that's the third line of this matrix. What do we have in the third line of this matrix?
The rotation of the robot doesn't correlate with the position of the landmark.
Exactly, and in this specific case, it doesn't, because here we are assuming that we have an absolute sensor. So the sensor is able to measure absolutely the x and y of the landmark in absolute frame. So it doesn't depend at all from the angle of how the robot is oriented. Okay, so that's the reason why we have completely uncorrelated x and y with the angle. In principle, in general, you will have some correlation, but it will be a weaker correlation. Or, I mean, it depends on how the robot travels, but there will be some part of correlation there, okay? So that's to give you an idea on why this matrix is structured in a specific way. And we know also that the whole graph becomes fully correlated, so if you just try to trace to build a graph out of the covariance matrix using as an adjacency matrix is fully dense. The same applies for the inverse of the covariance matrix, as we've seen for the Seif. It's actually dense, but just with very low edges. And here you can see some of them are weakly correlated, some of them are very strongly correlated. Okay, so that's somehow the values that you get in your covariance matrix. But in principle, everything is fully correlated. Now, in terms of complexity, we have cubic complexity in the measurement dimensions. This comes from the update rule because we have to invert a covariance matrix that has the dimension of the observation. It has every step is dominated normally by the number of landmark, because every time we need to multiply with the covariance matrix, which is this Q quadratic with respect to the number of landmarks, and we cannot escape this kind of complexity. Exactly. And the same is for the memory consumption, because we have to store all these numbers somewhere, and this is n square numbers. So this is just an O of n square. In practice, this will be 3 times 3, 9, plus 2n squared, so 4n squared. But when we talk about asymptotic complexity, the only thing that actually grows is the number of landmarks over time, because the pose is still the same, will not change over time. So the message, take-home message is that the Kalman filter works pretty well because we are building systems that actually are quite fast, quite reliable, with low uncertainty. It has, it's a good solution, very easy to implement and to use. But if we start to go to very high dimensional problems, very huge, large maps, it doesn't scale well with the number of landmarks. So it scales quadratically with the number of landmarks, which means that we might only be able to use it for small, mid-size environments, but not for city-scale environments or quartiers or large chunk of the world. Okay, so there are two main limitations of the Kalman filter. One is the way we linearize. We can try to find a better way of linearizing. We have seen that linear first-order Taylor expansion is actually not that great for high uncertainty and highly nonlinear function. And the second thing is the efficiency. So to address the linearization part, we show that there is a better way to linearize the system. And I mean, I can ask you, what's the answer to that? Anyone wants to say? So, exactly. So we have seen the uncertain transform, which then goes back to the uncertain Kalman filter. Okay, and how does it work? The main thing that you have to keep in mind is that when we do a Taylor approximation, we only consider the mean. We transform the mean and we transform the covariance accordingly, as it will be a linear function. But when we do the uncertain transform, we have a set of sigma points. So we consider information which is a bit away from the mean and comes from a second order concept, which is the axis of our covariance matrix. So they are like a quadratic form. So an ellipse here is a quadratic form. No? It comes from the isolines of a quadratic X transpose some matrix X. No? And then we move each of them. Okay, and then we recompute the parameters of the best quadratic form that estimates there, and we end up with something like this. So we end up with the different mean and the different covariance matrix that with the Taylor expansion. It turns out that the mean is actually the same because we are using, in both cases, the exact function to move the mean. But what actually is important is that the uncertainty is computed differently. So here we have a better approximation of the covariance matrix than we will have in using the extended Kalman filter, so the Taylor expansion. So in principle, the UKF will give us the same results as the EKF for linear model, because when we have a linear model, there is only one way of propagating the uncertainty. It doesn't matter how you do it. You're going to end up in the same way if the algorithm is actually computing it correctly. When we have nonlinear model, then the UKF has a better approximation of the EKF. Okay? But sometimes the differences are so small that it doesn't really matter from practical purposes. But what matters is that the UKF does not need to have any Jacobians. Okay, so if your measurement function or if your motion model are coming from an algorithm of some sort of complex function that it's hard to differentiate and to find the Jacobian, you can still use the UKF because it just needs to have a pointwise evaluation of your function. But if you want to use an EKF, you need to write down your Jacobian. Of course, you can do it numerically, And if you do it numerically, you're starting to get close to what a UKF does, because numerically you take some directions and you just take the difference and you divide it by the offset. And I mean, according to how you put them away, you're kind of starting to get something similar. Or at least you get the same complexity of the UKF with a worse approximation. And it doesn't really make sense. Okay? So, in terms of asymptotic complexity, it's the same, because the sigma points are proportional to the number of landmarks that you have. So it's basically a linear complexity in terms of the number of landmarks, because you have 2 of them and you just need to put them down. So it just adds a multiplicative factor on the asymptotic complexity, but doesn't really influence it. So it's still n squared. And in practice, like this lower, because you need to compute these sigma points, you need to propagate them, and so this is an overhead that you have in the system anyway. Okay. The third thing that we have seen is the extended information filter that actually works on a different parametrization of the normal distribution. The typical parametrization we have is the one based on moments. So we have a covariance matrix and a mean. But we can also get an inverse parametrization, which is based on the information matrix and the information vector. And as we've seen also later before, this just is a way of rewriting the exponent of the Gaussian in just changing and shuffling a bit the values around. Okay, this has an importance also in machine learning and in statistics, because those parameters here are what's called the natural parameters of distributions and are connected to the concept of sufficient statistics. For the Gaussian case, you have this mapping between 1 and 2, so you can also use this as sufficient statistics. But for other distributions in the exponential family, you really write them in terms like this. So you have a polynomial on top of your exponent, and all the parameters are the coefficient of the quadratic, or if you have a cubic or whatever part of the exponent, the linear and the constant part, and so on. Okay? So that's how the sufficient statistics of distribution can be expressed. And what we've seen that this EIF, so the extended information filter, is basically the equivalent of the Kalman filter when we work directly on this parametrization. Okay? And we have seen that instead of computing now this sigma and mu, we just compute directly omega and xi. And we have a conversion between these two, and the complexity and expressiveness is roughly the same. It's just that the 2 steps, predict and update, they change the complexity between each other. The predict step becomes more expensive in an information filter, while the update step becomes easier. You can still use the same trick of the inversion lemma for the information filter, so you can still exploit this low rank update of your information matrix during an update of the system. But the main problem, and the reason why the extended information filter is not so widespread used in practice, is that you don't have an explicit mean that you can play with. So you don't have explicitly the value or the expected value of your random variable, which is something you normally want to know because it encodes the position of the robot, the position of the landmarks, and also you need that for doing linearization. Okay? Therefore, when you just have a generic system where you cannot exploit any structure, normally you don't use an information filter. What happens, so if you see, this is basically I just told you that, the difference between the two. If you instead have a system that you know the structure and you can play around with sparsity, you can play around with conditional independence, and you know that something actually can be approximated very well, which is the case of SLAM, then the information filter becomes interesting to explore. And the reason is that you gain efficiency by considering the sparsity of your distribution. Okay? And that's what we've seen actually today at the end, that if you look at the estimate of a SLAM problem with respect to the different landmarks and the path of the robot, you see that we have a very dense covariance matrix, also a dense information matrix, but with a lot of values which are close to 0. Okay, so that's what the structure that we exploit for the information filter. We've seen that to exploit this, we basically informally divide the set of landmarks in terms of active landmarks, passive landmarks, and then landmarks that move from active to passive. And we see that the strong links we want to keep, and the weak links, so anything in here which probably connects something in there, we want to remove away. The sparse extended information filter has a similar structure to the Kalman filter, plus two main steps which are added. One is the update of the state estimate, because we still need to recover the state estimate, but instead of just multiplying with the inverse of the information matrix, we solve it a least squares problem. And since it's a sparse least squares problem, it's also efficiently to solve, and we'll see how to do in practice towards the end of the lecture, the class. And the second step that we need to take into account is the sparsification step. Now, we want to cut these links of the landmarks that were active at some point in time, and then they become passive in a second point in time. Okay? And for cutting this, we show that how it means that we need to update few values of the information matrix, and magically, when you update them, they become 0, and which is equivalent of saying I cut this edge in the resulting graphical model. Okay? So why we care about this? We care it because it's efficient. Since we have a sparse structure, we only need to maintain links between the robot and the landmark for a small set of landmarks at the time, which is this bounded set of active landmarks. We remove then links between the current pose and old landmarks, which are the one that moves from the active to the passive, which basically means we are making an assumption, or we are making an approximation where we say we just declare these two variables in the state space to be conditionally independent on the active set. Okay, so that's what we are saying in terms of approximation there. This in turns also bounds the number of links between landmarks in the passive set, because if you remember, the reason why two landmarks gets correlated or linked while doing a SLAM in this extended information filter is because you marginalize the pose. So everything that actually then was connected to the previous pose and the current pose gets connected to the current pose and gets connected to all the landmarks that were before. If we cut some of these links, basically we are isolating one landmark to be then correlated to the rest of them. And therefore, bounding the robot landmark connection also bounds the landmark to landmark connections. Okay, so this basically means we can keep the matrix sparse and roughly bounded so that we can have a roughly constant time update of the filter. The difference between Seif and AKF SLAM, or UKF, because in these terms is something on the same level of complexity, is that we're basically trading off efficiency with accuracy. We have, can you see? So we have a roughly constant time update. For now, we're just seeing something where we have known correspondences. So we haven't looked at cases where we need to compute the correspondences between the landmarks and the state estimate, because in principle, if you do it naively, you have to check for each variable in your state space if this is the one that actually you're observing right now. So you have linear complexity. There are better ways which have logarithmic complexity if you build some kind of structure, but let's say it's constant time for non-correspondences. That's what you should know right now. We have a linear memory complexity, and that's because the amount of non-zero values in the information matrix, it's proportional to the number of landmarks, but not to the square of the number of landmarks, since we are bounding them. And we do not need to store the zeros in this matrix. So we just store a list of non-zero values, And we don't really have a full dense matrix, but we just have a list of lists, basically. That's how you store sparse matrix in memory. But on the downside is that we have an inferior quality of the results, but for most of the practical issues, this loss in quality, it's not too much, it's not too big. Therefore, it's worth to have a strong gain in efficiency and memory consumption with a small loss in accuracy. Okay? So that's basically the end of today's lecture. So we have seen all this algorithm, Kalman filter, extended Kalman filter, unsanded, and the information filter. They kind of show the broad spectrum of possible ways of addressing the slump problem when you assume a Gaussian random noise. And we have seen that this one here has the assumption of linear motion and linear observation, so normally it's never used in practice unless you really have a linear problem. Those two are actually quite similar. They end up in very similar results for moderate level of noise and moderate nonlinearities, but the UKF is actually better at handling nonlinear functions. And from a complexity point of view, they're actually in the same family of complexity. We have seen the extended information filter, so the non-sparse version, which is roughly in the same level of complexity of the Kalman filter and ascending Kalman filter, but it's just more complicated to implement naively. And if you need to consider the mean for estimating the nonlinear approximation of your problem, then this gets even harder because you have to invert a huge matrix, so it gets cubic instead of quadratic in the size of the state space. But the interesting thing is that we can exploit some structure of the problem and still have an information form, and we end up in what we said, the sparse extended information filter that exploits the structures and can create a trade-off between efficiency and accuracy towards the goal. The whole thing that they have in common is that they all, let's say, require Gaussian distributions, or put it differently, they assume that the noise that you have comes from a Gaussian distribution. If your noise doesn't come from that, or specifically if your noise might be due to different phenomena, so it's kind of a mixture of Gaussians or it has multiple ways of explaining it, then you cannot use any of these approaches. Or you can use them, but you lose a lot of guarantees because they will just end up in making a Gaussian approximation of your error, and you will just end up somewhere. Now, in case you have two modes, you can decide to either commit to one of the two, or you can decide to take the full, like the mean and the covariance of the full distribution. The reason that we say here they require Gaussian distribution is that the input of the algorithm itself is either the parameter of a Gaussian in terms of mean and covariance, or the parameters of a Gaussian in terms of information matrix and information vector. And they represent the state space also in terms of a mean and the covariance. So they never have any other way of representing the distribution, but the inherent distribution is a parametric form, and those parameters are actually the parameters of a Gaussian distribution. Okay? So we'll see that there are other ways of handling distributions which are non-Gaussian, and we'll see it from next week, I think in 2 weeks or next week, when we'll talk about the particle filter and so non-parametric filters for arbitrary shaped distribution, functions, and noise. Okay? So that's it for today, and as I promised, we finished 15 minutes early, so we get the break now. Yeah, if there is any question, just ask, or we can finish here.
So those filters are for unimodal cases, right?
Yeah, so those filters are mainly for unimodal case, and you can, so they require as input a unimodal noise, and if you don't have a unimodal noise, you need to come up with something that somehow represents it. But also in terms of belief, they always express one mode in the belief distribution. So they will commit to one solution, to one mode. And there's no guarantee if you really have a multimodal distribution that this will be the correct one. There might be like a suboptimal one.
So all those filters can use for full SLAM or can only use for online SLAM?
So in principle, you can use it for both. It's just that they will be very computationally intensive to use the Kalman filter for full SLAM because you're just exploiting the state space. If you work on, okay, it's quite interesting. So the way I presented them and the way they're used in the literature mostly, it's for online SLAM. There is one small twist. There is a version of the sparse extended information filter, which I believe is called sparse extended delayed state filter or something like that, where you show that if you're having a full SLAM problem, so if you apply an information filter on a full SLAM problem, the sparsification is actually exact and is not an approximation any longer. Okay? Intuitively, you can imagine that we, let's say, the way we break sparsification or sparsity in the information matrix is because we are marginalizing the previous pose, right? If you never marginalize the previous pose, then we never have a fill-in in information matrix. And when we say that we don't marginalize the previous pose, we're actually addressing the full SLAM problem. So that's not in the class, but if you want, you can have a look at that. I think it's called exactly sparse delayed state filter or something like that. If you're interested, I can give you, send me an email, I can pinpoint to the paper on that. But the whole idea is basically, instead of it being an approximation, it's exact. So you have a larger state space, but you still have a very nice computation because it's still linear in the state space. And if you think that the number of poses somehow correlates with the number of landmarks, then you still have something which is n, no? If they are roughly on the same level. So the asymptotic complexity is the same. You don't have any problem in the with respect to approximations because it's non-approximate, it's exact same thing. But you have a slight overhead because your state space, instead of being n, is 2n or 4n, I mean, depends on which is the multiplicative factor. But you have more variables there, but you have less zeros anyway. So in some way, it's the same property of the Seif with respect to efficiency, but without the loss in accuracy. But that's not part of the class. So if you know it, it's good. It's good for you, but you don't have to know it for the class. Any other question? Okay, so then see you next week.